Hello everyone. Today we are going to solve problem 2.1 from Irodov's book on problems in general physics. But this video is not just about finding the answer. Along the way, we will uncover a very beautiful idea hidden inside this problem. An idea that engineers use in leak detection, gas storage systems, scuba cylinders, and many industrial applications. So make sure you stay till the end because after solving the problem, we'll zoom out and discuss where this concept is actually used in the real world. Let's begin. The problem states that a vessel of volume 30 liters contains an ideal gas at 0 degrees Celsius. After a portion of the gas has been let out, the pressure in the vessel decreases by 0.78 atmospheres, while the temperature remains constant. Find the mass of the gas released, and the gas density under normal conditions is given to us as 1.3 grams per liter. So let me draw it out. We have a rigid vessel containing gas, and the volume of the vessel is given to us as 30 liters. The temperature of the gas initially is given to us as 0 degrees Celsius, which is equal to 273 Kelvin. And let's say that the mass of the gas in this vessel is m1. Now, some of the gas from this vessel is allowed to escape. So I already drew out the initial condition, and now let us move on to the final condition. The volume is the same. The temperature is given to us as 0 degrees Celsius. It does not change. So it's 273 Kelvin. And since some of the gas is allowed to escape, the mass of gas in this situation is now m2. And we do not know what m1 is or m2 is. Not yet. So the temperature has remained constant, the volume is constant, and at first glance this looks like a straightforward ideal gas problem. Most students immediately write PV is equal to nRT, where P is the pressure, V is the volume, N is the number of moles, R is the universal gas constant, and T is the temperature. However, before doing any calculations, let's stop and think. What is changing? The vessel is rigid, so the volume remains constant. The temperature is also given to be constant. Now we already know the equation PV is equal to nRT. Since V and T are constant, this implies pressure is directly proportional to N, which is the number of moles. And since number of moles are directly proportional to mass of the gas, pressure is proportional to the mass of the gas. Now let's solve this problem. The density of the gas is given to us as 1.3 grams per liter. So we've already been given the density, which is 1.3 grams per liter. And the volume of the vessel is 30 liters. initial mass of the gas, therefore, m1 becomes density times volume, which is equal to 1.3 times 30 is equal to 39 grams. So this is the initial mass of the gas in the vessel. The pressure decreases by 0.78 atmosphere. So when we go from the initial state to the final state, we have delta P is equal to 0.78 atmosphere. The density that is given to us under normal conditions. So initial pressure would be 1 atmosphere. P1 will be equal to 1 atmosphere. And delta P is given to us as 0.78 atmosphere. And since there is a drop in pressure, we can say that P2 will be equal to 0.22 atmosphere, though I don't think we'll need to use the value of P2. I think we'll be able to do it using P and delta P. Since pressure is directly proportional to mass, we can write down delta M upon M1 is equal to delta P upon P1. This will give us delta M is equal to delta P times M1 divided by P1. If we lock the values in this equation, we get delta P is 0.78 atmospheres, M1 is equal to 39 grams that we calculated over here, and P1 is equal to 1 atmosphere. This gives us the value of delta M as 30.42 grams. And that is our answer. But now let's do something more important. Let's climb above the maze and look at the bigger picture. The key idea we discovered was for a rigid vessel at constant temperature, pressure is directly proportional to mass. In other words, pressure itself becomes a measure of how much gas is present inside the container. This simple idea has several practical applications that we are going to discuss now. Industries detect leaks in pipelines and storage tanks by monitoring pressure decay with time. Compressed air systems in factories are routinely checked for leaks by observing pressure changes. Scuba divers estimate the amount of breathing gas remaining inside the cylinder simply by checking the pressure gauge. Engineers also perform decay tests to verify the integrity of tanks, valves, and piping systems. So the next time you look at a pressure gauge, remember, under suitable conditions, pressure is not just pressure. It also tells us how much gas remains inside the container. Thank you for watching. If you enjoyed this video, please consider liking and subscribing. I am building this channel around mathematics, physics, scientific ideas, and explaining from first principles. And if there's a topic you've always wanted to understand, let me know in the comments. It might become a future video. See you in the next video.